What are limits? Limits are a concept that, in my experience, some calculus students struggle with. They're kind of what all of calculus is based on. They represent the distinction between calculus and all the math that you study before you get to calculus. And so they sort of represent a new way of thinking that can take a bit of getting used to. So in this video, I'm going to try to explain the concept behind limits by giving you an analogy. So I'm not going to show you any mathematical symbols or formulas or equations. I'm not going to talk in this video about how to actually find particular limits. I'm just going to try to explain the concept behind them. So, suppose you have a digital image on the screen of your phone or TV or computer monitor, and it has one bad pixel, one bad point, because there's one bit of the image file in your computer or on the DVD that you're reading from that's been corrupted somehow. So there's one bad point that the computer or whatever's displaying the image doesn't know what color that's supposed to be. So it tries to guess what color that pixel should be based on all the other nearby pixels. So if all of the other pixels around that bad pixel are the same shade of orange, then it's a good bet that that bad pixel was supposed to be orange too. And so what we might say in math language is that the limit of the picture as you approach that particular pixel is that particular shade of orange. Now this still applies even if it wasn't a bad pixel. Maybe that pixel works just fine. Maybe it was already orange. The limit is still what color the pixel should be in order to match all the other nearby pixels. So if that pixel is already orange and all the other nearby pixels are that same shade of orange too, orange is the limit. And if the pixels on one side are a slightly darker shade, the pixels on the other side are a slightly lighter shade, and the one right in the middle, if you can tell what that should be to make a nice smooth transition, that's what the limit is. If that particular pixel that you're looking at is purple, but all the other nearby pixels are orange, then orange is still the limit. So the limit doesn't depend on that particular point, just on what all the other points nearby are. Maybe that particular point was supposed to be purple for some reason, or maybe it was purple by mistake. Maybe it got corrupted somehow. But it doesn't matter what color it is. What matters is what color it should be to fit in with all the other nearby points. If that pixel or that point is undefined, if it doesn't have a color assigned, it really is a bad pixel, but all the other nearby pixels are orange, then orange is still the limit. And like I said, if the pixels on one side are a slightly lighter shade of orange, and on the other side are a slightly darker shade of orange, but you can fill in that middle pixel, that bad pixel in the middle with a shade of orange that's right in between and provides a smooth transition between the shades on either side, then that intermediate shade of orange is the limit. But if the pixels on one side are orange and on the other side are black, and it's not a smooth transition from orange to black, it's just a sharp boundary line between, okay, they're orange on one side and they're black on the other, then you can't tell what color that particular point should be to match all the other nearby points. There is no one color that matches all the other nearby points. If you make it black, it doesn't match the nearby orange pixels on one side. If you make it orange, it doesn't match those black pixels on the other side. So in this case, there is no limit. We would say the limit does not exist, because there is no one particular color that you can assign to the missing pixel that will make it fit in with all the other nearby pixels. Now, for this to really be analogous to limits in calculus, you have to assume that the image has infinite resolution. That you can keep zooming in farther and farther. And each pixel, each point on the screen is a single infinitely small point, and there are infinitely many of them. And there's no such thing as one pixel being right next to another, because if you zoom in enough, you can always find there's space in between them where there's room for lots of other points between those two. So if the limit at a particular point is a particular shade of orange, that means that all the other nearby points have to be almost that same shade of orange. There may or may not be points that are exactly that same shade of orange, but they all have to be very close. If there are points nearby that are a different color, like black or pink or a much darker orange, as long as you can zoom in some more so that those other colored points are outside the region you're zoomed in on, then you can still say that the limit is that shade of orange. So as long as you're somewhere in an orange region or an orange stripe, even if it's close to the edge, you can zoom in enough so that all you see is orange. But if you were right on the borderline, on a clear, sharp border between an orange stripe and a black stripe, then no matter how much you zoom in, you're still going to see some orange and some black. That is, some points that are a very different color than other points, and so the limit does not exist. There is no one color that you can assign to that point that would make it seamlessly fit in with all the other nearby points. Now, some more calculus terminology here. If the picture, without fixing or reassigning any bad pixels, is already nice and smooth transition, we say it's continuous. So if a particular pixel is already the right color to match the other nearby pixels and fit in with the image, we could say that the image is continuous at that point. Otherwise, it's discontinuous, or we would say it has a discontinuity. And if it's the kind of discontinuity that we could fix by changing or assigning the correct, appropriate color at that point to be what it should be to match all those nearby points, that is, we'd assign the color to what the limit is, then we would call that a removable discontinuity. We could remove the discontinuity and make it continuous there just by changing the color at that one point. Otherwise, it's a non-removable discontinuity. So a point that was right on the line between two sharply different colored regions would be a non-removable discontinuity. Now, I promised you at the beginning that I wasn't going to show you any mathematical symbols or equations or anything like that. If you want me to keep that promise, you can stop the video right here. But in case you've seen the official formal definition of a limit as it's presented in calculus textbooks, the infamous delta epsilon definition of a limit, I'm going to go on and show you that and try to explain how the analogy that I've just talked about relates to that definition. So, the definition, the official formal definition of what it means for the limit as x approaches a of f of x to equal some number L looks like this. And in my analogy, the f of x is the color of point X on your image. And the A that you're looking at the limit at that point, that's the particular point we're interested in, like the point where there's a bad pixel. And then the L, what the limit actually is the particular shade of orange for point A to match all the nearby points, if there is such a particular shade of orange. So sometimes there is a limit, and sometimes the limit doesn't exist. But if there is a limit, here's how it's defined. It means that for every epsilon greater than 0, there exists a delta greater than 0, such that whenever 0 is less than x minus a is less than delta, or sorry, the absolute value of x minus a, then the absolute value of f of x minus L is less than epsilon. So here the epsilon represents how close to that particular shade of orange you're sort of required to get. And the delta represents how much you zoom in. So what this is saying in this formal mathematical precise language is that as long as you zoom in close enough, all the nearby points will be very close to that same shade of orange. How close is very close? Well, as close as you want to get. You can pick any degree of closeness, and for any particular degree of closeness, you will always be able to zoom in enough so that once you're zoomed in that close, all the points that are nearby to point A will have their color nearby, close in color to that particular shade of orange that you said was the limit. So that's my attempt to explain what limits are. Hope this helped. If it didn't, leave me a comment. If there's anything I can explain any better. And thanks for watching.